I would like to maybe try to visit a bit of the differences between the scientific Python world and, say, the web development world or the sysadmin world, because I think that this is actually the strength of Python. If I look back over maybe 15 years of doing Python for me, coming from other languages, what Python has really brought to me is that it wasn't a scientific language. And that's maybe a paradox for somebody doing science. So this is a bit what I'm going to try to go through. And this is the first version of first time I give this talk, and because my team has been keeping me very busy for the last few weeks, I haven't had time to prepare it much. So bear with me. This is more of a reflection, ongoing reflection. Okay. So the first thing is data science. I think you've all heard about it, but data science these days is fairly hot. The data scientists have been said to be the sexiest job currently in the planet. So the good news is Python is one of the most popular languages for data science, maybe the most. If I look back, so I was doing data science before it was called data science and before it was cool. And I was also doing Python in science before it was cool. So if I look back, I think one of the reasons why Python is such a good tool for data science is because we have this mix of culture. And that's a bit what I'd like to walk through. And years and years ago, when I would give a scientific Python talk to a general audience, people would go like, oh no, my God, we're not going to understand anything. We don't care, it's boring. On my end, when people talk database, I'm like, oh, I don't understand anything. But bridging this gap, me understanding database, which I understand a bit by now, and maybe you understanding the basics of what we do is, I think, really important for what's going to give us an edge. And so one thing is, if you want to earn more money, you become a data scientist, but I guess that's just, who wants to earn money anyhow? I'm in academia. Okay, so how did it happen that Python got hot for data science? Well, it happened because we built good tools. I'm one of the early contributors of scikit-learn, and other people did pandas, but these were built on good foundations. So now maybe we see these tools, but these tools were built because we had the right basic to build it. So the first thing is, yes, there is a culture gap. Scientists come from Jupiter, and web devs, they come maybe from Saturn, and they're also sysadmins. But the fact that we can work together is at your strength. So let's explore a bit this culture gap. Well, the first thing is we're different. So you guys, I don't know, what's your core data? Well, strengths maybe. I mean, that's what I feel. I just do numbers. Floating point numbers. I feel comfortable with floating point numbers. And I put them in arrays. What do you use to store your data, to manipulate? Databases. Yeah. I use arrays with numbers. You guys do object-oriented programming. Well, I do that sometimes, but not really when I do my main work, which is science. I just use arrays. Flow control? Oh, come on. You'd be surprised. Some people don't use flow control. Not saying they're good programmers, but we just use arrays. So there's a bit of a culture gap. And actually the culture gap makes it that often it's fairly hard for you to understand this world. Whereas often we think, I say we, but I've done web devs, I've done applications and everything. I'm just putting on my lab coat today. So a lot of scientists just don't see the point of all this anyhow. So why would they bother? They're wrong, by the way. All right, how about we do something together? How about we do something useful? Web dev and scientists get together, and how about we sort the EuroPython website? So we agree, the EuroPython website, that's a web dev thing. It's not a, scientific Python thing. So currently there are 173 talks and counting. And if you look at the title, they're very, very various. There are a bunch of talks on data science, by the way. So how about we use data science to find some common topics through this? And I'm going to walk you through this process. So what we're going to do, we're going to start by scrapping all this from the web. So I could have asked the EuroPython guys to give me the list of talks, but it was way more fun to scrap it from the web. It's more realistic. Then I'm going to get a text description of all these things, and then I'm going to do some text mining on it to get word clouds, and those word clouds are going to tell me, which talk goes where. I did this script, and it's, I think, 150, maybe 200 lines of Python code, nothing more. With the whole thing, from web scrapping to storing, to outputting the clouds, the word clouds. So for the scrapping, I'm going to use joblib too, Python standard library, and I'm going to use beautiful soup. And for the rest, I'm going to use scikit-learn. Nickname is scikit-learn when you import it, and word cloud, which is a small module by Andy Mueller, who does word clouds. So the first thing, I crawl. Now this is your typical, at least for me, it's your typical web dev problem. For you, no, that's not completely true, but that's fine. And so I've crawled the thing to get first, from the schedule, I will get a list of talks and URLs. And from the talk page, each of these URLs, I'll download the talk page, and I'll crawl again to get the abstract and the tags. So I have this. I have basically one dictionary that is giving me title to textual description with tags and all this. I have another one that's giving me URLs if I want to come back to the URLs. So if you've never used, who has never used beautiful soup here? Nobody? Cool. You guys are not scientists. Who does data science numerical stuff? 1, 2, 3.
I don't know.
Ooh, I feel better. That's not a lot, though. Good, then maybe you'll learn things. I won't teach you scikit-learn. I usually do this, so I won't do this today. So that's the first thing. The second thing is we're going to do something that we call vectorize, right? So these are strings. As I told you, I'm not comfortable with strings. We could go back to this. There's a core reason why I'm not comfortable with strings. So we're going to convert them into floating point numbers, which I am comfortable with. And for this, we're going to build a table of terms. So what are the words that are present? And in each document, I'm going to count them. So I'm going to have a term frequency table. So maybe A is the word that's most frequent, followed by the, and then, this is an example. So if I want to look at the topic of this talk, well, the most frequent word won't be terribly useful, right? Neither A nor the is terribly frequent, is terribly useful. So then what I'm going to do is I'm going to count over all the documents of my database. I'm going to count those terms, the present of those terms. That's going to give me what we can call the document frequency. So you can see that over all the database, the is the most present, followed by A. And then I can do the ratio of these two. And then the one that's relatively most present in my database compared to the rest of the document, maybe is the one that's driving the meaning. So maybe this talk is about profiling or performance, but it's not about code or module, okay? So this is what we call vectorizing in general. So we go from data that is not numeric to a vector of numeric data. That is something absolutely core to data mining and machine learning, all these things. And there's a good reason, by the way. There are not many scientists here, so maybe you want to close your ears. But this lives in a vector space. I can do math in a vector space. I can do linear algebra. I can do statistics, whether it's on paper or in a computer. And really what we're seeing across the history of data analysis is that you're going to want to throw things in a vector space. Okay, parentheses closed. So this may be known as a bag of word. Sometimes we call it a bag of words. And the way we're really going to do this is that we're going to do what's called a TF-IDF transform. So a term frequency versus inverse document frequency. It's something very common in text analysis. And the way you can do this in scikit-learn is that you've got something that's called scikit-learn.featureExtraction.text. So this is all our text feature extraction. And then you have a TF-IDF vectorizer. So it's something, you give it a list of text and it returns numerical data with which we can work. So what it returns is really a 2D matrix that gives us, you can think of it as an Excel file, for instance. The columns are the different words, and the rows are the different documents. This is, by the way, what we call our, so this is known in text analysis, this is known as the text document matrix, but this is really what we call our data matrix in scikit-learn, and we're going to convert every data to this, because that's a universal representation of many different objects. They could be anything. They could be documents, they could be people in a database, they could be just anything. Images, by the way, by features. So what are the different numerical features that I described them with? Okay? So when we've fallen back here, I feel comfortable. I'm in my world. I can do what I usually do. Which, by the way, is true. I don't work with the text data, I work with image data, and I only work with numerical matrices. So one thing to note, maybe keep this in the corner of your head, is that this can be a sparse matrix. Terms can be very infrequent. So one term may be almost a no document. The speaker's right here, so I need to be careful. So then I'm going to have mostly zeros in my matrix. And it may be useful to store it when not storing the zeros. Yeah, Chris is looking surprised, but suppose you know, and this really happens in text. You may really want to store the rare words because they carry a lot of meaning, but they may be present in less than 1% of your document. And the bigger, by the way, the bigger your database grows, the more you tend to have this. You know, a very rare word that carries a lot of meaning. So you're going to have columns that are mostly zeros, and you might have a lot of them. So then you want to store this in some form of a compressed way. You know, you can fill this. But then it's going to become a huge matrix. And so we store them, we decided to store them as sparse matrices. And sparse matrices are things that have been used hugely in engineering and numerics. And there are different, you know, it's a whole world of itself. I won't go into these details. But it's going to come in handy later because we're plugging in things that already exist, right? So then, I told you we were going to find topics. Then what we're going to do is that we're going to factorize this. And the idea being, that's the intuition. You know, you have your text document matrix, and you're going to factorize it into a product of two things. You're going to factorize it in a product of a topic matrix, so a topic to word matrix, and a topic to document matrix. What the topic to word is telling me really is, given a topic, what are the terms that are important in this topic? And the other matrix is telling me, given a document, what are the topics that are expressed in this document? Okay, so if you're afraid of math, you just look at these yellow things. But this is really mathematical formulation of what we're doing. Once we have this, I can solve this using linear algebra, for instance. Matrix factorization is a very common linear algebra problem. Or I can solve this using optimization routines. Anyhow. And often what we do is that we impose non-negative constraints because the fact that a term is negatively loaded in a topic may not be very useful. So that's something that's used hugely in in topic learning. So you can do this with scikit-learn.decomposition.nmf for non-negative matrix factorization. Okay? So we run this. And we get a set of topics. So our first topic is this. It is basically a representation of the topic. The bigger the word, the bigger the weight in the topic. So this is a topic that I would call probably MISC, because it's a general topic about nothing very specific. Now that's a second topic. I think this is a topic about machine learning. You look at the different things. This is really, by the way, your Python website. It's kind of fun. So yes, all this kind of makes sense. in terms of machine learning. Third topic, well, people are interested in testing too. And then, I can run all of them, and now if you can read all of them, you don't need glasses. But there are topics about web development, there's the topic about the Python interpreter, there is a natural language processing that's here. Here we have scientific computing, here we have concurrency, so it kind of worked. All right? And I hope I've demystified it. I hope now you've understood how basically we go from text to numerics and we run this. You want to try it? Okay, the first thing you're going to do is pip install scikit-learn. All right, what's going to happen? Bang, it's going to break. Well, probably, yes. It's going to tell you, NumPy is not installed. All right, pip install NumPy. Bang, it's going to break. It's going to tell you something completely incomprehensible. So that's where I lose all my friends.
You should use binary from Golang, probably, Golki.
Yeah, sure. There, of course. There are ways around this. But we're going back to the cultural difference. When you're going to break, this is really going to happen to you. You're going to break because the Fortran SO, and actually I didn't put the Fortran SO 3GF, is not installed. And then you're going to go, what? You're still using Fortran? Well, you know what? Fortran gives us the fastest linear algebra routines. And between a fast, a good atlas, which is linear algebra, and a non-fast one, you might have a factor of 70 times. We're talking, compiled libraries, 2 different compiled libraries. We're not talking 2 different non-compiled libraries. So if you're talking big data, this matters. So packaging is a major roadblock for scientific Python. It's for you when you try to use it, and it's for us also. Now the good news, so this is fundamental. This is nothing easy. Nobody's done a sloppy work here. The problem is that we're using lots of compiled code, and this is not going to go away soon. This compiled code comes with shared libraries, and shared libraries that are not, Python libraries. There's a set of shared libraries that call each other. So we're in C world. And then when you fight with library and ABI incompatibility, we really do. When they upgraded GCC, at some point they changed the ABI of Fortran and everything broke. Now there's progress. There's a huge amount of progress. So there's been all kind of intermediate solutions, like Christoph Kolke's binaries or the various binary distributions like Anaconda. But really, I have a lot of hope in the many Linux wheels. So wheel first was absolutely fantastic. Wheel allows you to ship binary. And then second, many Linux, that's a PEP, mostly by, I don't really remember his first name, McGibbon and Nathaniel Smith. And the idea is that you're going to rely on a very conservative core of libraries, and then you're going to embed all the rest. And this is becoming a standard, and hopefully many Linux, I think many Linux has made it to PyPy. So with this and with the rest of wheels, we're getting there. And one last thing is that OpenBLAS is a pure C, non-Fortran, fast linear algebra that's getting there. So hopefully pip install, all these things will work really soon. It's starting. Okay. So I told you some people don't use flow control. Let's look a bit at how we, the people in the lab coats, work. Well, first, we absolutely love NumPy. And here's one example. I have a list of 10,000 term frequencies, and I want to compute the ratio between this and the document frequency, okay? So the fastest way to do it in Python with lists is this. You build a list comprehension, and you use the ezip from InterTools. And so it takes half a millisecond. It may not seem big, but actually 10,000 is not a lot. 10,000, is 100 documents by 1,000 words. That's tiny. No, it's 10 documents by 1,000 words. So even the 100 documents by 1,000 words is 10 times more. So the way we do it in NumPy is that if TF is a NumPy array and IDF is a NumPy array, all we have to do is to compute TF divided by IDF, and that's going to do it, element by element. And we can see that it's approximately 20 times faster. That's good. It's pretty good. And this scales pretty well. You know, if you crank up the size, the difference stays the same. And if you're in tiny sizes, your Python overhead basically is kicking in. In terms also, something I didn't mention on this slide is that in terms of memory usage, the memory usage of the list is much bigger than the memory usage of the array. So let's look at, okay. Yeah, before we look at why arrays are good, there's another thing that we like, is that we think that this is more readable than this. It's a question of training, really. When I started doing array computing, this is array computing, it's present in many other places, MATLAB, R. When I started doing array computing, it took me a little while to train, but this is much more compact. Okay, what's an array? You can think of it as just a fancy pointer. You have, what a NumPy array really is you have a memory address, you have a data type, you have a shape and a stride. So really you've got this block of data, and what really the NumPy array is telling you is what's in there and how do I go from one element to another. So I can go in one direction like this, I can go in another direction like this. This is just an offset. How much do I need to jump from one element to go to the other? And the shape is telling me, well, if I'm jumping, at some point I should stop jumping, or I'm going to go outside of the memory block. Okay? So what we really have here is a memory block, the pointer to it, and a description of how to walk around it. So it's nothing but a fancy pointer. And in the memory, it's actually stored, it can be stored in a different way because you can, you know, modify shape and strides and everything, but it's really something flat. Okay? Now, this is crucial because it matches the memory model of just about any numerical library, just about any, and many other things, by the way. So any data that can be represented in a regular way can be represented this way. Not strings, by the way, but there are tricks to get strings in there. For instance, you can store hashes of strings, and that works extremely well. People have been doing this extremely well. Okay, can you remind me how much time do I have?
Oh, I don't think I can do it.
You can't do it. Okay, well, when you can, please do.
Yeah.
Okay, so this is crucial to us. The fact that arrays are nothing but pointers is what really makes all our computing good. How many time?
15 minutes at all to do questions.
Okay, very good. So I need to speed up a bit. Okay, now, a limitation of the model is if I try to do this TF divided by IDF and I try to remove 1, for instance, what will happen is that Python is first going to compute TF divided by IDF, and it's going to store it in a temporary file, temporary array. So here we have 2 times n items that move in the CPU, 1 times n here, 1 times n here, and then n out, n that move out. And then I'm going to take this temporary thing and I'm going to remove it 1. So I'm moving n items in, n items out. So can you see the problem here? The problem is that we've been moving too much data in and out the CPU because we've really been moving n items out, the temporary files, that didn't need to. And the CPU is much faster than the memory, including the cache. So really this n thing, this extra n, so this extra temporary, is not at all what we would want. And I can illustrate this if I time. So if I look at how much time it takes to do TF divided by IDF, I've taken bigger arrays here, so it's 200 microseconds. Now if I look at how much time it is to do the same thing, subtracting 1, it's almost twice, which is consistent with this. Now, if I create a temporary array, and then I do an in-place modification, which means that there is less data that moves in and out, then it's significantly faster. So by basically deconstructing the bytecode and doing the operations myself, I can make things faster. So that is a limitation of the high-level array computing model. So it's extremely terse to write. It's very condensed. You can read it very easily, but it doesn't give optimal movement of data. So a C level for loop would be closer to this speed. All right. So to take a step back, this is a very similar problem to grouping SQL queries. If I'm going to do multiple queries to a database, if I can group them together and do operations in the database rather than retrieving the data and doing the operation myself, it's going to be much faster. This is something I don't know very well, by the way. This is addressed by a set of different packages, but each time with a bit hacks. You can use string expressions. You can write this as a string and numX will compile it. You can do a bytecode inspection with numba, or you can use lazy arrays. Now I told you we didn't use control flow. So what if you need an if? Here's an example. I'm dividing TF by IDF, but I don't want to divide by zeros. So if it's 0, I want to output zeros. So I can do it this way. First I create a TF IDF, and then TF IDF where IDF is 0, I put it to 0. Can you understand this? It's just a selector. Other example. Suppose we're looking at ages in a population. I can compute the difference of the age for gender equals male versus gender equals female I wanted to put. Okay? This is real code. This will run, by the way. So this is starting to look very much like queries on a database, isn't it? And so for these kinds of things, especially these things where you're manipulating heterogeneous data, there is something that's called pandas. That's basically something that's between arrays and an in-memory database. And so for me, who don't understand well SQL, it's actually a struggle to understand pandas. But I guess for you, yeah, I don't know SQL. I'm starting to now. So pandas is really good for queries, it's less good for numerics. Okay? So to wrap up on this part, numerics versus database, numerics are efficient. That's really important to understand that numerics are efficient because they're regularly spaced with them. So basically this makes good noise memory access for the CPU because the cache prediction works just fine. But if you really have big data and big queries, then a query language and compilation of this query language to optimize the query plan can actually be useful. And in R, there's actually something that's called dplyr that does this, that exposes an array-like interface, but that does compilation of query plans. So that's interesting for me because it's the world of web dev that is kind of creeping in my world and making me feel insecure. But now, if you're going to do statistics or machine learning or data mining, you're going to be doing numerics. And that's, as I said, it's because it's vector space. And it's important, so that's a little detail, but people go into very sophisticated engineering to do out-of-core numerics. It's not that important because basically you can have very good streaming algorithms that are used in the fancy things like deep learning. The idea being that you process data chunk by chunk. Okay? So Spark, which is not Python but is extremely famous in the big data world, actually combines very well a distributed store and a computing model. But because it doesn't have this, structured, regular space data model, if the data fits in RAM, the Python world is faster, quite clearly. So are we seeing the end of compiled code? So for scientific computing, it was stuck in Fortran for so long, and it's actually moving a lot to Python, so that's pretty good. The Python VM is great for this, and the reason it's great is because it's simple. So Java and .NET have things like software transactional memory, which is great because it allows you to basically not have locks, and then have parallel computing works extremely well. But for what I do, it's actually a lot of problem because I really want to use foreign memory. I do this all the time. And interestingly, Java is gaining this to work in the Hadoop ecosystem, the data ecosystem. The reason being that copying memory in and out the Java virtual machine is terribly costly. The other thing is, I hear a lot of people from virtual machine research that tell us that our garbage collection is not great because reference counting will create locks. Well, the nice thing is that when I program C code, I can very easily manipulate the reference counting of the Python VM. So part of the reason why Python got so big in science is because the VM was fairly transparent. It has a clear C API. Another thing that's crucial is reflexivity. Okay, so in the Python VM, I can modify, I can interact with everything. So debugging, of course, debugging is crucial, but we work in science and data analysis, we work hugely with interactive work. So this is possible because in Python everything is, you can manipulate everything from the inside. So analysis of code, I think, is something that's happening more and more. Persistence is crucial, and I guess the ORMs use this a lot. And parallel computing, it's not obvious that parallel computing needs this reflexivity, but it does because it's using persistence basically. Because when you're moving objects from one computer to another, you need to persist them and move them. So, in my opinion, if it's not pickable, it's not Python. And I see people writing code that are not pickable, it's going to work. So one thing that we use a lot is basically memorizing big data to disk. And there's something that's called joblib that we wrote, and it's basically a two-disk memorizer, so you can decorate a function, you give it something that is big, and it's going to dump it to disk, and if that something that is big is holding most of its data in a NumPy array, it's going to be efficient. Why is it going to be efficient? Well, partly because it's going to pass the pointer to, say, a compression library instead of passing the data and copying it. Okay? And it's not calling, it's not the Python code basically that's doing the persistence. And we can also do out of core with this. So I said I wouldn't talk about scikit-learn, but just a few words. One thing that has made it hugely successful is that we have a simple object-oriented API where you create an object, you call it a classifier, it's your magic object that's going to be able to predict. You give it data, you call fit, and then you call predict. And this is universal. You have to understand this, and I'm going a bit fast, so you're not understanding the details. But you can use this on every single object, every single algorithm of the library. This means that you can basically switch data mining strategies. And this is something that has made scikit-learn hugely popular. And this is possible because Python is an actual rich language with a good object-oriented programming model. One last thing, Python. Who knows about Python? Yeah, that's good. Python has been huge for us. First, you can take code and make it faster by, for instance, adding type, and then you're getting the benefits of compilation, which is not only speed, but also robustness. Unlike other things that do, just in time, like Numba, Python, if you manage to build the library, if I give you a binary, I'm pretty sure it's going to run right. And then the second thing is it allows us to call external libraries extremely easily. People don't realize, but it's super easy to bind things with the site. So it's not quite the end of compiled code, but the thing is, I don't do any pointer arithmetics anymore. And pointer arithmetics is what has been killing me when I do compiled code, because they're so hard to debug. Because I allocate memory in NumPy, and then if I ever have to do compiled code, I do it via Python, and via the Python NumPy API that allows me to safely go through the memory without going out of the array. Okay? So we're happy. We have database, we have numerics, we're happy. I think there's a lot of future to the Python data ecosystem. How can we make it? Well, the first thing I'd like to say is that machine learning is going to be more and more present. I'm not sure how much you're aware, but you're going to be using it, whether it's hidden in libraries or whether you're actually aware of it. So who knows about Elasticsearch? All right. How do we get Elasticsearch in Python? This is something serious. How do we get Elasticsearch in Python? In Python, I mean, not bindings. I'm not sure because I don't know it well, but I think that for our future, it's something important. And then the second thing is, we're going to get machine learning in this because, as I've shown you with topic modeling, statistical analysis is going to allow you to identify patterns. It's going to allow you to make better search. It's going to allow you to correct user inputs. So what I'm telling you here is that what I've talked about, the numerics, you may not really care about the details, but I really hope that it's going to make your world more powerful. So a few crazy ideas, and then you're going to tell me if I'm talking complete nonsense. So parallel computing in Python has good and bad things. The first thing is that multiprocessing in futures actually work extremely well. So you all know about this, right? The idea is you span a new Python process to do parallel computing. But the thing is that the overhead of process creation and communication is present. It's not huge, but it's present. And sometimes it's the limiting factor. And the other thing which is really a killer is that this leads to data duplication. If I have a very big data in one process, I have a very big data in the other process. And I can work around this, but it's extremely tedious and not portable from one OS to another. Now here's the crazy idea, and we can discuss it offline. How about we have several virtual machines, Python virtual machines in the same process? So Python level fork. If this happens, then these two problems go away. And we don't have to make the VM crazily complex. The other thing I'd like is more code analysis. I'm extremely happy to see type annotations come. I think probably Python will be using them in the near future. The idea is that with type annotation you can do compilation. And the other idea being that with type annotation maybe you can do just-in-time analysis. And so convert part of the code to LLVM. Or just assume that things are NumPy arrays, for instance. If you've annotated things as NumPy array, you just assume they're NumPy arrays. And if they're not, because type annotations are only indications, if they're not, it's fine, you fall back. Now if we do this, suddenly we have extremely powerful computing in standard Python, no Python. So I'm not sure how we can do this, but I think it'd be great to have better support for code analysis in the standard library. So I think I'm on time, I need to wrap up. So I've tried to take a step back and try to see what we have in common and different between web development and scientific computing. So I think the biggest culture gap comes from compiled code. And my friend web developers often told me they didn't care about compiled code at all. And I guess that was true for a long time. But more and more we're going to have data analysis that goes into web applications to have rich web applications that have better behavior for the user. So I think we're going to have to care about this. But the good news is that the packaging ecosystem has been improving hugely and will continue to improve. So thanks to the Python Packaging Authority. So I think there's an interesting parallel to be made between numerics and array computing and databases. So I'm still trying to understand this parallel, but I think it's there. And they have different data representations. So the database data representation is less structured because it's more made for random access, so typically using trees. And they also have different execution engines. And that's the reason, because when you use a database well, you basically build a SQL query or you build some form of query and then you send it to your database and the database run it. Whereas with arrays, it's the Python VM that runs this. I think, and that's just an intuition, that there is a lot to be done in uniting those ideas better with a Python virtual machine. And in a sense, something like the IBIS project. So do you know about the IBIS project? It's a project by Wes McKinley, the guy who did Pandas. And he's basically, it's got some reminiscence of PonyORM, which is to be able to write expressions in Python that can that can get then compiled to SQL and then executed on a distributed store. So that's really, really nice. That's the future. But Python is making it hard for these tools. So Blaze is another project like this. And what I didn't talk about is that you can actually use machine learning now. You can try scikit-learn. There's a bit of a culture gap, but it's not that bad. And I tell you that in a couple of days you should be productive. Thank you.
Thank you very much. Any questions? Okay, it was another one clear talk. Okay.
Yeah, thank you for the talk and for the job you do in Python. It's awesome. And by the way, I partly understand it. Yeah, you are saying like, well, let's pretend I don't trust you because I don't know what you do exactly in all those projects. Why should I use that project, scikit-learn or something, some wrappers around C code instead of just taking C or C++ by hands?
Is your question, why should I use compiled code because it's very hard to audit and I can do crazy things in compiled code? Or is your question, should I just wrap my stuff myself?
Yeah, should I just do it myself?
Scikit-learn is actually very little compiled code. Because of the things I've shown you, you can actually write extremely efficient code, mostly in Python. But the reason why we can do this is because we have the compiled code, right? So because we have NumPy, because we have scipy. I mentioned at some point sparse arrays. So sparse arrays were present in scipy before they were used for data analysis. They were used for other things. And so all these are actually compiled code. But most of the lines of code of Python are Python code. Of scikit-learn are Python code. So your question is, scikit-learn is not a wrapper around C code. It's Python code that uses a bit of C code.
Yeah. I must be talking about that. To write, you're saying that to write efficient code in Python, I need to think about that, and that things. But if I do C code, I just do efficient code that I like teach to write.
Okay, so your question is, why should I be doing basically this word Python code instead of just to be doing C code? Well, it's hugely more productive in terms of human time. First, you don't do any memory management. And memory management, and this is not a joke, memory management in my experience is what is most costly in terms of time when you do numerics and low-level languages. And this is not a joke, by the way. I've seen many situations where people would simply allow the when they would allocate the memory on the heap, not on the stack. So basically, create big globals and then not worry about it, which of course doesn't scale at all to complex problems. So the first reason is you won't have to do memory management. If you're doing memory management with this stack, you're doing it wrong. The second reason is the code is just much more brief. It's much more condensed. I'm writing TF divided by idea. I'm not writing, I as an integer for I in blah. So it's much more readable. And then the other thing is, Python comes with battery included, but scipy also comes with battery included. All the linear algebra is there, and binding to linear algebra is hard, really hard, because it uses C++ and Fortran. So you're there, you're in a productive environment. And that's why we're seeing this transition from low-level code from Fortran to high-level Python code.
Thank you.
Yeah, thanks. Okay, I think that's all. Thank you very much.